Alright, in this video we are going to do the last section of chapter 11. So I told you this was going to be a really quick chapter because one, it only has 3 sections, and the two, we're just trying to move a little faster. So this section is on the second and third laws of thermodynamics. Okay, so and here's just the restating of the second law of thermodynamics. When objects of different temperature are brought into contact, the flow of thermal energy is always from the higher temperature object to the lower temperature object. And we learned that in the last chapter as well, that things flow from hot to cold always. Okay. So let's move this up. The second law of thermodynamics is more restrictive than the first. The first just says you can't create or destroy energy. Well, now it's trying to tell you exactly how that energy is going to flow from hot to cold. The second law says that all processes that conserve energy only proceed in a particular direction, again, from hot to cold. In a sense, the second law implies the directionality of the behavior of nature. It always goes in one direction. So sometimes it's referred to as the arrow of time, but that's just to say. All right, so here's an example. Figure below illustrates this directionality. If an egg is dropped to the ground and splatters, you know that that's what's going to happen. It's going to drop, it's going to hit, crack, and splatter. It never happens in the reverse process. You don't see that splattered egg come back together, get back in the shell, and go back up to where it dropped from. That process just never happens. Another way that we've stated the second law of thermodynamics is that everything in the universe tends towards more disorder or towards more chaos. And that example shows that the egg's going to break and splatter rather than get back together and become a solid egg again. That would be being more organized. Everything tends towards more disorder rather than more order. Okay, so the second law always is also in reference to the efficiency of engines. This is why engines can never be 100% efficient. Some of that energy is always going to be lost as waste. Now, it's not destroyed, it's just not usable anymore. So we call it waste, and that lowers the efficiency of the engine. So this connection between energy efficiency, or engine efficiency, and the second law of thermodynamics was discovered by Sadie Carnot. And we're going to talk about the Carnot cycle in a little bit. But Carnot said, what was the maximum efficiency in engine operating between a hot reservoir at TH and a cold reservoir at TC? That's what he was wanting to figure out. So he arrived at what is now known as the Carnot's theorem, which states that a heat engine operating between Kelvin temperatures TH and TC will have its maximum efficiency. It won't get any higher than that. And here's the equation. Whoops. Whoa, there we go. Here's the equation for that. Maximum efficiency is equal to 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. There always has to be a change in temperature in order for the engine to do work. Okay. So Carnot's theorem is important for a number of reasons, so we're going to list these 4. It means that no engine, no matter how sophisticated or how advanced, will ever exceed its maximum efficiency. And it doesn't matter what type of engine this is, what the engine is made of, or how it's constructed. All that matters is that there's 2 temperatures, 2 different temperatures in order for this to work. So make sure you know those, and there'll be some more on the next page. But make sure you know that that's what makes the Carnot theorem so important, is that you can never, no engine, no matter what, will ever be exceed its maximum efficiency. And that's the 1 minus TC over TH. And then it doesn't matter what type of engine it is, doesn't matter what it's made of or how it's constructed. All that matters is that you have 2 differences in temperature. Okay. Only temperatures of the hot and cold reservoir are what determine an engine's efficiency. Again, not what it's made of, not how it's constructed, nothing like that. It's just what is the temperature difference between the hot and the cold. That determines the engine's efficiency. When hot and cold reservoirs have the same temperature, then we have zero efficiency and the engine does not do any work. Okay? So we have to have a temperature difference in order for the engine to do work and in order for you to have an efficiency greater than zero. This means that heat engines always operate on a temperature difference. Heat engines always operate on a temperature difference. Okay, so here's an example from the book that illustrates Carnot's theorem. So we have a heat engine is operating at its maximum efficiency, 0.288 or 28.8%. The cold reservoir is 295. What's the temperature of the hot reservoir? So again, we're just going to plug into the equation for maximum efficiency, and we're going to rearrange to solve for TH here. Oops, that's all they did. So algebraically, you're going to multiply both sides by TH. And then you are going to divide by Emax. And you're going to get rid of the 1. Okay? So you're just getting, no, I'm sorry, that is so wrong. Let's try not to do this in my head. Let's write this out. So if I want to solve for TH, I'm going to need to multiply everything on both sides by 1 minus TC. Nope. Get it right, Amy. Let's do it this way so I can see this better. Okay. There we go. So the TH is on the bottom. So to get rid of the TH, I'm going to multiply both sides by TH. So those cancel, and I'm left with 1 minus TC equals TH times Emax. Well, I'm going to divide by Emax. Okay. And that's going to get rid of that and give me TH equals, and we're going to have to clean that up a little bit when I divide by Emax. Let's get rid of that right there. Okay. So I want the TC, so yeah, I think those are just inverses of each other. There we go. All right, so then I'm going to substitute those values in for TC and Emax and solve, and that gives me 414 Kelvin. All right, so this should bring back memories for chemistry anyway. Delta S, entropy changes. In chemistry, we talked about enthalpy, and then we also talked about entropy. We're just going to focus on the entropy part. So in physics, the quantity called entropy is a measure of disorder in the system. Entropy is related to the second law of thermodynamics in that disorder is always increasing. And here's the formula for calculating entropy. Delta S is equal to the amount of heat given off divided by the temperature. According to this definition, when thermal temperature is added to a system, then Q is greater than 0 because we're adding energy, we're adding heat. Q is greater than 0, so the entropy will increase. So if Q is greater than 0, entropy of the system increases. For example, water heating and boiling is converted to steam. That increases the disorder of the molecules. So going from a liquid to a gas, you are increasing the disorder because in the gas phase, they're all kind of random and going everywhere. whereas in the liquid phase, they're a little more organized. When energy is removed from a system, then Q is less than 0 and the entropy of the system decreases. So an example of that would be freezing water in order to make ice. So the liquid molecules are a little more disorganized, but when you bring them down and lower and remove that energy and get them moving slower, they begin to get in a more organized crystalline structure. And so you are going from more disorder to more order. Okay, now that doesn't, okay, anyway, I'll leave it at that. All right. Key feature of entropy is that no process can decrease the total entropy of the universe. Okay, so entropy of the universe will never decrease. It's always increasing. The best thing that any process can do is leave the entropy unchanged. That's the very, 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 very best we can do, is to not change the entropy. But other than that, entropy is always decreasing. In terms of entropy, the universe moves only in one direction, and that's towards increasing the entropy. And that's the same thing as restating that second law of thermodynamics. So entropy is always increasing, or the amount of disorder is always increasing. All right, so the third law of thermodynamics is that you can never have something actually reach 0 degrees Celsius. It is impossible, or 0 degrees Kelvin, sorry. Oops, let's go back. There we go. Okay, so this is our third law of thermodynamics. It's impossible to lower the temperature of an object all the way down to absolute 0. That is unattainable. That's the third law of thermodynamics. You can get close, but you don't actually get there. All right. So just as a recap of these 3 laws of thermodynamics that you need to make sure you know, the first law states basically you can't get something for nothing. We can't create energy, we can't destroy energy. The second law states that the best you can do is possibly break even, or states that we can't even break even, that we're always going to have some energy be wasted. And the third law states that no object can be cooled all the way down to absolute 0. Those are our 3 laws of thermodynamics. And that is it for chapter 11. So we will very shortly be having a test on this and move on to electricity. That's what I think we're going to do next. And then we'll finish up the year with waves.